All right, so again, we're continuing on with relativity because it's all relative. And so what we're going to look at is something called length contraction. All right, so again, what I'm going to do is look at one situation, but again, from two different perspectives. Perspectives in physics is frame of reference. All right, so this situation I've got going on, again, we're talking about extreme speeds and such. So consider a spaceship making a trip from planet A to planet B. So here's planet A, and here's little planet B over here. All right. Now, again, I'm going to use the fact, I guess a little recall. Oops, recall. I am going to use our formula. D is equal to V times T. Or again, that's just the formula V equals D over T, just rearranged. All right, and the other thing is that the spaceship is traveling at a speed of V. All right, and well, let's see here. So what we're going to do again is look at some different situations. And so when I look at my observer, so this is a perspective of from the planet. All right, so from the planet, we're watching the situation of this spaceship travel from one planet to another. All right, now for us, the distance from one planet to the other is called LS, because that is the length that this person who is stationary, i.e. this person here on planet A, would measure. Because that planet B and A, they're a distance of LS apart. So if this person on Earth could take a measuring tape and measure across, they would get distance L. And because nothing's moving to them, it's called LS. Now, the distances that spaceship is traveling, or sorry, not the distance, but the velocity is still V. That's not going to change. Now, to this person on Earth, this spaceship is moving. And so the time is T, but TM, because they are watching that spaceship move. So again, LS, whoops, why does it always go big? So LS is equal to, again, the distance measured by the observer on Earth, or on planet A, I guess you should say, or B, because neither one of them are moving. So I'll go with planet A because that's where I have my person. And our time, TM there, again, is the time measured by the observer, again, on planet A. Because, again, the spaceship is moving to them, but yet the planet is not. All right, so we got a TM and a TLS, or we got an S term and an M term in the same formula. We haven't had that before. All right, so that's the situation. All right, that's one perspective. Now I'm going to flip perspectives, where I'm going to look from the spaceship's point of view. All right, so there's my little astronaut on there. And again, the same scenario that's occurring is that this spaceship is traveling from one planet to another. All right, now, TS. Well, how are we going to look at this? Again, I'm going to use my D is equal to V times T. Now, the distance. Here's the crazy thing. The distance that this person here on the spaceship, so I'll put them in red there, when they look at the distance between the planets, this is kind of a hard concept to get a hold of here, is that from them, when they look out the window, they think Earth's moving, or say that's what it looks like. They think this planet A here is moving away from them. That's their perspective, right? And because they look out the window, they're like, wow, that planet is getting smaller and smaller. It's moving away from me. Then they go out and look out the front window, and they look at this planet here, planet B. And so to them, the distance between them and that planet is moving towards them. That's the way they look at it. And so my distance when we're measuring between planet A and planet B for the person on the spaceship is called distance LM, because to them, the planets are moving, even though that's not true, right? But that's their perspective. Now, the velocity of the spaceship, well, you look in the speedometer, it's still going to tell you the spaceship is moving at a velocity v here. Or in their case, it would appear that the planets are moving at a velocity v, right? So that's their perspective, is that the planet would be moving, planet A would be moving away with velocity v, and planet B would be moving towards them with velocity v. So that's the way they look at it. Now, the time that it takes, again, they're in the spaceship, is our TS, stationary, because to them, the spaceship's not moving, everything else is moving to them. All right, because for the astronaut in the spaceship, so they would be considered our stationary time. All right, so again, a little bit of, let's see, right here. So LM, again, this is a situation where planets are appearing to be moving relative to the observer on the ship, right? But here, the TS, again, this is a situation where the spaceship and clock are not moving relative to the observer on the ship. Well, again, it's all perspective, right? So this person sees this ship. Hey, we're just standing still. This planet's moving away from me. This planet's moving. Planet B is moving towards me. That's what's happening. All right, now here's our formula. Now here's what I'm going to do, a little substitution. Is that we got therefore, I'm going to make, again, a substitution here where I'm going to use our formulas from our first period and substitute that in. So instead of TS here, I'm going to put TM times the square root of 1 minus V squared all over C squared. And again, that's just as earlier today. I just rearranged the formula because we had TM is equal to TS divided by the square root of 1 minus V squared over C squared. So I just rearranged this formula there. So now I plug that in. All right, now let's see here. Now I'm going to make another substitution. All right, so and therefore my LM is going to be equal to LS, because I want everything in terms of lengths, times my 1 minus V squared all over C squared. And this is just as we looked earlier just now, that LS in our first perspective is equal to V times TM. And so here's our formula right here that we're looking at. So it's all, again, perspective. Is it things moving or are things stationary? Now, kind of a fallout for this formula is that, well, we'll get to that. So let's have it, well, here we go. Is that for someone observing the length, I guess, or something, or an event in motion, the length seems shorter because the object, well, is moving. Let's just go with that. So for someone inverting event in motion, the length seems shorter. All right, so how does that play out? I'm going to go to example 2, actually. first is that here's a great example. A comet traveling past Earth with a speed of 0.7 c. So it's a nice way of saying 70% the speed of light is measured to be 2,000 meters long by observers on Earth. What is the actual length of the comet? All right, so again, I'm going to use my formula here. I'm going to write her down. We got Lm, all right, is equal to Ls times 1 minus, these are hard to write with a mouse. Man, it's killing me. V squared divided by c squared. All right, so again, c is always the speed of light. That doesn't change. That's going to be, let's see here, 3 times 10 to the power of 8 meters per second, standard units. All right, now our spaceship, or no, our comet, I should say, is traveling at 70%, or what we say is 0.7 c. Now we get to two different things here. We got Lm and Ls. All right, Lm and Ls. Now, when this comet is traveling past Earth, it's measured to be 2,000 meters long by observers on Earth. Now, if that comet is traveling past Earth, to us, it is moving. So I'm going to put Lm as 2,000 meters. What I want to find out is what happens if I'm traveling on the spaceship? If you've ever seen the movie Armageddon there, get on an asteroid or something. What would be the actual length? And this is kind of stuff they have to think about when we try to, because recently I think it was just like a few months ago, we actually traveled and tried to land on a comet. It's the first time they've ever tried to do stuff like that. All right, so you got to kind of take into account how long it really is. All right, so I'm going to substitute in my values here. So my Lm, 2,000 meters long. All right, Ls, and let's see here. So we got 1 minus V squared is 0.7 c, and I square it, divided by c squared. All right, so let's see here, simplifying things here. So I got 2,000 here. All right, equals to Ls. All right, let's see here, 1 minus. Now, when I go here, 1 minus, I got up top, I'm going to have to square the 0.7 and square the c squared. Now, when I square the c, I'm going to have a c squared on the top and a c squared on the bottom, easy for me to say. And so essentially, they divide each other out. And so I'm going to have a 0.7 squared here. All right, so again, just simplifying, I got 2,000 long. That's what it appears to look like. Ls. And let's see here, 1 minus, or I got to go 0.7 squared, 1 minus that. I take the square root, and 2 decimal places, I get 0.71. All right, now I'm going to divide both sides by 0.71. And so my Ls, and again, I think Lily, you asked this question, just like my TM and my TS, they got to be in the same units. So it doesn't matter what units we use, they just have to be the same. And so when I take 2,000, I divide it by 0.71, I get 2,800.56 meters. So if I went and stood on that comet, it would be 2,800.56 meters long. But since we're on Earth and we're watching it, it looks smaller because it's moving. And that's why this is called length contraction. It looks smaller because it's moving to us, or relative to us, it is smaller. Again, relativity, perspective. All right, now let's try one more of these guys, a little bit different. A UFO is orbiting Earth at a high rate of speed and is first spotted when it passes a communication satellite orbiting 3,280 kilometers above the Earth's surface. Now, after investigation, it is calculated that the actual orbiting distance was 3,770 kilometers. How fast was the UFO traveling relative to Earth? Whew. All right. So again, I'm going to use my formula here. Let's get this down. LM is equal to LS times 1 minus, let's see what we got here. V squared over C squared. All right. Now, C, well, again, C is the speed of light, right? So that's our 3 times 10 to the power of 8. That ain't changing. Meters per second. V, we want to know how fast this UFO was traveling. A couple weeks ago, one just flew over an airliner, actually. Kind of crazy. Now, we got LM and LS. Which one is which? Well, it says that when it's first spotted, it appears to be this far, 3,280 kilometers above the surface. But they can actually calculate the actual distance was 3,770 kilometers. Now, there's a couple ways to look at this. The first one is that the actual number, just like the comet, where it was actually 2,800.56 meters, this one here is our actual, so this would be considered our LS, which then, of course, means this is our LM, because this is when it's first spotted where it's moving. And then after investigation, they figure out what the actual distance was. So now there's another way of looking at this, is that if you understand that length contraction means that if we observe something moving, it looks smaller. And so it's always going to be your smaller number. So that's another way to look at it. So there's my 3,280, the small number. This time we're dealing in kilometers. And here is the length, the actual length, if nothing's moving. I don't know if I should say actual length, relative length with there's nothing, no motion. All right, so now I'm going to, I'm going to substitute into my formula here. So I got LM here, which is my 3,280. Again, they're in the same units here, LM and LS. So I got a 3,770 kilometers here. Let's see here. What do we got under here? Same old, same old. 1 minus V squared over C squared. I'm not going to plug in C yet because it's scientific notation. It's a little bit annoying. All right, so what can I do here? Well, I want to get V by itself. That's what I'm trying to solve for. So the first thing I'm going to do here is I'm going to divide both sides by 3,770. Whoops, 770. And so those divide those out right there. All right, and so let's see. I take 3,280. I divide it by 3,770. And 2 decimal places as usual. I get 0.87. All right, and then over here I get, well, the square root of 1 minus V squared over C squared. All right, again, a little math work. Well, the easiest thing I can do here is let's square both sides. That'll get rid of that square root sign. That's annoying. So let's square both sides. And so when I square 0.87, what do I get here? 0.87 squared. 2 decimal places. I'm going to go with 0.76. All right, well, squaring undoes the square root. So now I've got 1 minus V squared times C squared. I got a fraction there. What am I going to do there? I'm going to move. All right, so again, there's lots of ways to do this, simplifying and solving. I'm going to move this negative V squared over C squared to the other side, and I'm going to move this 0.76 to the other side. So when I move my negative V squared divided by C squared over to the other side, it's now going to become positive V squared over C squared. All right, now I have a 1 over there, but now I'm moving this 0.76 over, so, well, now it's a minus 0.76. All right, getting there. All right, so now I've got V squared, because that's what we're trying to solve for, v, right? C squared, I know that number, or I can find it out. 1 minus 0.76, well, I get 0.24. Now, what I got here is a number equaling a fraction. I'm going to go fraction equaling a fraction. And so 1 times v squared is v squared. Now that's equal to 0.24 times c squared. All right, now let's see here. So, well, all I have to do now is, well, take c squared. Oh, I got v here. All right, so let's see here. I'm going to square root both sides again. All right, so that gets rid of the 2 on the v. I have to square root 0.24, and I have to square root c squared. Well, square root c squared is no problem. Square rooting 0.24. Again, to 2 decimal places, I get 0.49. And then again, square rooting c squared, I get just c. Again, I know what c is. 3 times 10 to the power of 8. So my velocity, I take my 0.49. All right, I times it by 3 times 10 to the power of 8, and I get 1.47 times 10 to the power of 8 meters per second. And there we go. So I was able to, by measuring distances that the spaceship's traveling, we can calculate what the velocity of that spaceship is traveling. But again, the key is that if something is moving and you're watching it move, it will appear smaller. That's the key. And yet, time-wise, your time will take longer, or will be shorter. Time's shorter when you're watching something move for you, but yet the spaceship would be shorter. So kind of an interesting concept of relativity. Again, it's all about perspective, and that is the key with relativity.